Thanks very much for attending, everybody, and it's great to see the level of interest in the webinar. I'm Mark Stone, Integrity Services Manager with Sonomatic, and I'll be presenting the webinar today on statistical analysis of inspection data. We aim to share with you some of the basic principles, the benefits of the approach, as well as an overview of typical applications. So a starting point is looking at the role of inspection and integrity management. And obviously integrity management relies on knowledge of the condition of assets being managed. Decisions are made on the back of that knowledge, and the level of knowledge affects the effectiveness of those decisions. Inspection is obviously a key provider of information on the condition of assets on which you're going to base decisions. So if we look at sources of information that give you a view on asset condition, inspection is a significant provider of information. There's also information from corrosion, the corrosion control process and corrosion coupons and so on. You may also have models covering degradation. There'll also be process information. And that gives you a view on the condition of the assets both today, but you're also interested in the condition of assets, not just today, but also in the future. So how is asset condition going to evolve, because that'll affect your decisions. It's also worth saying there's a degree of uncertainty around asset condition. So you may be reasonably confident that that you've lost a certain amount of wall thickness, but there's equally some likelihood that the amount of wall loss might be larger than that. So there is a degree of uncertainty which relates to the amount of information that you've got. Based on the view on asset condition, you're going to be taking decisions around things like risk ranking. You may want to update the RBI, for instance. You would consider changing inspection intervals. You may look at reviewing the corrosion control system application. So for instance, you may want to increase or decrease the amount of inhibitor. Certain equipment items with severe damage, you may look at re-rating, or you may need to carry out repairs. So just very simply looking at how inspection provides information that affects decisions. If we look at these corrosion maps here, which are actually presented as wall loss maps. So blue material indicates a situation where there's very little wall loss, and red shows severe wall loss. So these three degradation states might be on different equipment items, but maybe at the same time through the life of the item. So this first case here shows low level damage from the inspection information. We may want to then revise the risk ranking downward, which would give us the option to extending the intervals. This middle one considers a case where there's moderate damage, and here we might want to review the risk ranking upwards if the damage is less severe than what we were expecting, or sorry, more severe than what we were expecting. We may want to carry out a fitness for service assessment to validate continued operation, or we may want to reduce the inspection intervals, for example. And finally, this here shows a situation where the inspection data shows severe damage, and in this instance, for example, we might want to replace this equipment item at the next opportunity. We may want to take other action like re-rating or reviewing an inhibitor strategy. So those are just simple examples of where inspection data allows you to make decisions. Integrity management needs to be effective, and basically what we mean by that is that it should allow you to take an action before failures occur. So information and knowledge are basically fundamental to that, to highlight that you need to take action before you get to a failure state. Obviously that's relatively straightforward when you've got a lot of information and complete knowledge of the asset condition. But in reality that's going to be difficult, because that additional information and knowledge comes at a cost, and we want to make integrity management also as efficient as possible. So you want to achieve the goals at a reasonable spend. So you want to have effective integrity management, no failures, but also without having to spend too much money achieving that goal. And generally there's a compromise between effectiveness and efficiency because of the additional cost of information. So in many cases, doing nothing would be the cheapest option. So you'd have high efficiency in terms of spend, but the effectiveness would be very low, and you end up paying for that through other costs like costs of failures and so on. Conversely, you can have a very effective process, but that maybe doing a lot of additional inspection activity, which then leads to reduced efficiency. But this compromise between effectiveness and efficiency doesn't have to be fixed as such. There are improvements that can be made by making better use of available data and information to enhance efficiency. So the knowledge that we have generally is going to increase with the amount of data or information available. So if we look at this graphic over here, the x-axis shows the information that we have available, which generally also increases. If we want to increase information, we're increasing cost. The y-axis shows the knowledge we have of the equipment, which feeds into effectiveness. So generally there's a tendency, the more information we have, the greater knowledge and hence effectiveness we have for integrity management. It is possible, however, to achieve, in a situation where we're just taking the data at face value, we might spend quite a lot on gathering information through inspection and other activity, but our level of knowledge still remains relatively low. We can achieve that same level of knowledge at much lower cost by doing more advanced analysis. So we basically improved, we've got the same effectiveness but increased efficiency just by doing more advanced analysis. And we've been able to achieve that by doing less inspection and hence less cost, for instance. Alternatively, for this same cost of getting that information, by doing more advanced analysis, we can improve the effectiveness by increasing the amount of knowledge. So essentially advanced analysis does give us options to improve efficiencies. And statistical analysis is really one of the keys to unlocking the additional value in information and data, and it's being used increasingly in integrity management for that reason. There's a wide range of applications of statistical analysis in inspection and integrity management, and just some examples would be statistical signal processing algorithms, quantified inspection performance, so things like defining probabilities of detection, assessment of probabilities of failure. Risk-based inspection systems are built around statistical principles, reliability assessments, corrosion growth rates, and so on. And also a large area is vessel non-intrusive inspection. A big part of statistical applications is around sampling inspection, which is going to be the focus of this presentation. So it doesn't cover all aspects of statistical analysis in integrity management, but focuses primarily on sampling inspection applications. So by sampling inspection, we basically mean an inspection where we're going to have less than 100% coverage. And that's often the case, that you're not going to do an inspection with 100% coverage, and it's often not necessary or desirable. In some cases, you may have restricted access, so you simply can't achieve 100% coverage. In other cases, you may want to manage the time and the cost of the inspection, or there may be other drivers for doing less than 100% coverage. It's worth saying that limited coverage inspections have been widely used, and the application of limited coverage inspections significantly predate the widespread use of statistical methods. You only have to think of pipework inspection approaches, for instance, where very often the coverage that is being done is less than 1%, sometimes 0.2%, something like that. And even though statistical methods aren't used in detail in a lot of cases, the principle is still that the inspected region is giving you some representative estimate of the condition of the uninspected regions. So the basic approach is that we would have a certain amount of area that we can carry out an inspection on and an uninspected area. So the question is then, can we use the data from the inspected area to make some estimates for this uninspected area? And the kind of things we might be looking for is, what's the expected minimum thickness over this area, and what's the probability that we may exceed some limiting condition? So what's the probability that the minimum thickness might be less, so the wall loss might exceed the corrosion allowance, for instance. So really what we're trying to do is make sure that what the information we get here gives us a reasonable view on what's happening in the uninspected area. So one of the fundamental requirements for a sampling inspection is that the data conforms to a statistical distribution that can be described parametrically. And what we mean by described parametrically is that the distribution can be fully defined just by a small number of parameters. So the data set that you collect might, for example, contain hundreds of thousands or millions or tens of millions of individual data points, and that defines the behavior of the area inspected. But what we're after statistically is to take all of that and try and condense it, capture its statistical behavior in just a small number of parameters, maybe 1, 2, or 3 parameters typically. So the parameters that we trying to capture based on the data that we've collected would typically, it varies according to the type of distribution, but typically what you're looking at is some kind of location parameter. So this graphic shows a probability density function, and basically most of the data is going to be within the range of this peak over here, and the location parameter would generally define whereabouts that peak is. So what's the most frequently occurring value, or gives you some sort of measure of a central tendency. Also important is not just, where's most of the data likely to fall, or what's the most likely maximum depth of a defect, for instance, but you also want to know something about the spread associated with the distribution, and that's defined by the scale parameter. So if we look at this distribution here, the width of the distribution basically is defined by the scale parameter. So a small scale parameter would indicate a tight distribution, so most of your data falls around a very narrow range, whereas a larger scale parameter would define a wider range over which you've got a lot of data. And then finally, there's other parameters like a shape parameter, which tells you something about something specific around the characteristics, like maybe the distribution is skewed rather than being symmetrical, and that sort of behavior is often defined by a shape parameter. But once you've effectively defined the parameters for the distribution, you can then quantify the statistical behavior overall. So in effect, once you know the type of the distribution and its parameters, you can then carry out statistical estimates. And just as a very simple example, if we look at the height of people, and we may have done a large number of measurements on a particular population group, that allows us to establish that the distribution is normal. So that's shown here in this sort of typical bell curve as such in the probability density function. So we've established that the distribution is normal, and the parameters for this distribution are a mean of 1.75 meters and a standard deviation of 0.07 meters. So the average basically is 1.75 meters, and the standard deviation tells us something about the amount of variability. So the statistical behavior is fully captured in these two graphics here. The one on the left is the probability density function, which basically the area underneath that shows the likelihood of a measurement in that range. And then the graphic on the right shows the cumulative probability distribution. So essentially this is a probability of shortfall. So basically what it's showing is that 50%, there's a 50% likelihood that any person from this population would have a height of less than 1.75 meters, and a 50% likelihood that it would be higher than that, would be larger than that. And as a probability of shortfall, it's basically also showing, for example, there's a 10% probability of a randomly selected individual having a height of less than about 1.66 meters. So also what it's showing us is that there's 25% less than 1.7 meters, and on the high side above 0.75, so 25% also above 1.8. So basically what that's saying is 50% of the population is likely to fall within a range of 1.7 to 1.8 meters in height. So there's a lot of information you can get from the distribution. So that lets us make some useful estimates. For example, if we took a randomly selected member of this population group, the most likely height is 1.75 meters, And also what we can say is that if we look over here, that there's a 0.3% probability, that's 0.003, so 0.3% probability that a randomly selected individual from this population would have a height of less than 1.55 meters, or conversely on the high side, also 0.3%, which corresponds to 0.997 of more than 1.95 meters. We can also start to look at things like, well, what's the minimum height? If we took 1,000 people selected from that population group at random and said, what's the minimum height likely to be? That would correspond to a probability level of approximately 1 over 1,000, so it would sit somewhere over here. So we'd say the minimum height, the most likely minimum height from 1,000 people would be 1.53 meters. And we can also start to say things around what's the likelihood that that minimum would be larger or less than 1.53 meters. So there's a lot of simple information we can gather just from the distribution. I'll try and show how that applies to inspection data shortly. So the basic principles of what we're doing with inspection data is very similar in that we measure the variable of interest over the selected area. Now, rather than measuring the heights of a bunch of people, we can use inspection to measure wall thicknesses or defect depths. The next stage is to establish the distribution parameters, or identify what the distribution is and fit a distribution to allow us to get the parameters. So just to give you an understanding of the kind of distributions that we're talking about in looking at inspection data, this slide here shows an example and hopefully sort of illustrates the basic principles. So on the right here we have a corrosion map over a selected area that's been inspected, and it's presented in 3D so you can clearly see where there's corrosion. In a corrosion map we typically associate colors with different wall thickness. So the blue material here would be material that's typically around the nominal thickness or above, and then going down to red, which would have some significant wall loss. So what we plotted in the way this is normally plotted as a distribution is as a cumulative thickness distribution as a probability of shortfall. So basically what this graphic is showing is that most of the material, because this is on a log scale, so most of the material, something like about 80% of the material, which covers this range over here, is at a thickness of more than about 11.5 millimeters. So that really refers to all of the uncorroded material. We see in this distribution a transition shown over here at about 11.5 millimeters, and then you get this tail forming, which covers about something like 20% of the area. So that there's about 20% of the area is affected by corrosion, and all of this material here, with the dots show, correspond to the color in the corrosion map. So we've got a relatively small amount of material at very significant depth, or a small amount of remaining wall thickness. So what this is showing is that we've got only 1 over 1,000, so 0.1%. So I've just been told that my mouse isn't visible on the screen, so I'm not sure I can point to. I wonder. Anyway, if you can try and follow from where it's 8 millimeters on the distribution to where it's 10 to the minus 3. So basically what that's saying is 1 over 1,000. In other words, 0.1% of the area is less than 8 millimeters. And if we go to 9 millimeters, that corresponds to approximately 1 over 100. So that means 1% is less than 9 millimeters, and then following up to about 10.3 millimeters, that corresponds to 10% of the material. So 10% of the material is less than about 10.2 millimeters in thickness. So in general, we'd be looking to generate distributions like this, and what we'd be doing is fitting a distribution curve to the tail of the distribution, which relates to the corrosion. So once you've measured that variable like we've shown in the previous slide and identified or developed the distribution, you then identify and fit a suitable distribution to that. You'd establish the parameters for the distribution and make estimates based on those parameters. The main requirements for doing a statistical analysis is that firstly the behavior should be statistically consistent. Essentially what that means is that the data that you've measured should conform to a distribution, and in general we'd be seeking to make sure that that data actually conforms to a distribution that's usually associated with some kind of physical phenomena. So the kind of distributions that would typically be applicable would be things like exponential distributions and Weibull distributions. Also, what we're seeking to ensure is that the region inspected should be representative of the overall area. So in other words, there has to be some degree of homogeneity so that your area that you've actually sampled from actually is representative of the larger, generally larger area that you wouldn't be doing the inspection on. And that's a really important requirement in order for statistical analysis to be effective. And then finally, the sample size should also be sufficient. So you want to achieve sufficient information in order to be able to make reasonable estimates. So a key issue is, does the corrosion behavior or does the inspection data actually conform to a statistical distribution and typically a statistical distribution that would normally be associated with natural phenomena. So the answer to this question is really provided by a lot of actual inspection work that we've carried out within Sonomatic on a wide range of different corrosion situations. So looking at things like pressure equipment with active CO2 corrosion, with active H2S corrosion, internal oxygen corrosion, external oxygen corrosion, so things like CUI, also pipe work with naphthenic acid corrosion in a refinery environment, under deposit corrosion, and across a wide range of petrochemical and minerals refinery vessels with acid corrosion. What we found is that distributions are typically regular and usually conform closely to one of a limited number of distributions, including exponential, Weibull, and log normal. Oops, sorry. So just looking at a typical example, if the corrosion map on the left here shows a separator vessel where there's corrosion mapping over quite a large area, and if you look at the corrosion map, it does appear fairly irregular and unpredictable. You've got some regions of significantly greater corrosion and larger extent locally, and then other regions of shallower corrosion and maybe smaller extent. But the wall thickness distribution for this case, as shown on the right, basically indicates that there's a significant amount of underlying order, even though the corrosion looks unpredictable. So the distribution on the right basically shows most of the material, in this case something like 90% of the material, is above 16 millimeters. And if there was no corrosion, that part of the distribution would continue to drop off fairly rapidly, kind of following a normal distribution as shown by the red line over there. So if you had no corrosion, the minimum thickness might be something like 15.7 or 15.8 millimeters, and there'd be no variation in that distribution. The fact that you get this transition point at around 10% and then this tail indicates that there is corrosion. Now the interesting thing here, and what lets you establish that it's an exponential distribution, is that tail, when plotted on a log scale, is pretty much linear, and that indicates that it is exponential, and because of that it's also indicating that there is predictable behavior. That kind of situation is widely seen with equipment suffering corrosion in service. So if we look at what that lets us do in terms of performing a sampling inspection, this slide summarizes how it would be applied to storage tank walls, for example. So you start in the top left graphic with an inspection scope with limited coverage. You carry out the inspection with corrosion mapping. You collect the corrosion mapping data. That corrosion mapping data is then analyzed to develop a distribution based on the data itself, which is as shown by the blue dots in the graphic. And then the next step is to fit a distribution to that the data related to the corrosion. So that's shown by the green line in the distribution. And once you've established that fitted distribution, you can then start to make estimates for a larger area than you have inspected. And those estimates basically relate to moving down the green line towards the left, and the level of the probability level or proportion of area basically defines an expected minimum thickness for a given amount of coverage. So the main distribution types that we use, the first one is exponential. This is quite frequently encountered in practice. What it indicates, and looking at this on a log scale, it is the tail tends to be close to linear on the log scale. And basically what that's saying is that most of your corrosion tends to be fairly shallow. In other words, most of the corrosion, the majority of area corroded, still has a thickness that's probably relatively close to nominal. And then as you move down the tail from right to left in the graphic, so the amount of material at that depth is becoming less and less. But because it's linear on a log scale, you still have potential for substantially lower minimums over a large area, because that tail would basically extend outwards to the left. In terms of what parameters define the distribution, it's fully defined by the slope. So in the graphic on the right, looking at the slope of that curve, if that slope drops very rapidly, then you've got much lesser likelihood of very deep corrosion. And the other main parameter is what proportion of area is affected by corrosion. So in this case, we can see that there's probably something around 10% of the area, corresponding to 10 to the minus 1 on the y-axis. That's where the transition point is, and something like that indicates the area affected by corrosion. So the exponential distribution with those two parameters defined will fully describe the tail distribution, and we can make estimates based on that. Another distribution that's frequently encountered in practice is a Weibull distribution. This is the main difference between this and an exponential distribution, is that the tail drops more rapidly with reducing thickness. And you can see that in the graphic on the right here, where the tail tends to continuously drop off as we move from right to left. And basically what that means is that there's a lesser likelihood of corrosion that's significantly deeper than what's measured. There does tend to be a sort of limiting depth for the maximum corrosion. The distribution fit in the case of an exponential is relatively straightforward, because it's just a straight line on a log plot. Distribution fitting for Weibull distribution is a bit more complicated because it has more parameters that you need to solve for. What we've talked about so far has been using what we refer to as an underlying distribution. In other words, using the complete corrosion mapping data set. And that approach is preferred because it retains the full information from the area inspected. It gives you more basis for carrying out comprehensive sensitivity studies. This approach, using the underlying distributions based on corrosion mapping data, was introduced by Sonomatic over the past 10 years, and it is now included in a HOIS Recommended Practice for Statistical Analysis. HOIS, for those of you aren't aware, is a joint industry project which includes participation from many of the major oil and gas operator companies, as well as inspection and integrity related vendor companies. So that approach is included in the recommended practice, and it is now widely used in practice for making estimates in the case of sampling inspection. The data that you need to use the full distribution isn't always available, obviously. There are cases where the inspection was such as to only record the minimum thickness. So, for example, if you were doing manual ultrasonics, you would only have the minimum thickness from grids and not a full data set. There are other situations where the surface conditions or other factors might limit corrosion mapping data quality, so that you can only get manual measurements from that data set at selected locations. So there are situations in which you don't have the full data set and you're looking for an alternative method for analysis in that case. And that alternative is extreme value analysis, which doesn't rely on a complete high density data set. The analysis methods behind extreme value analysis are more mature, and it's used across a wide variety of different fields, not just for inspection. And the analysis approaches developed in other areas are relevant to inspection. One of the issues, well, some of the issues with it is that it does lose information compared to using the underlying distribution, and your estimates may also be less reliable because you end up with smaller sample sizes in many cases. So looking at the basis for extreme value analysis, it is applicable to a wide range of underlying distribution types. So definitely to the two that we mentioned, the exponential and Weibull cases. But there are some restrictions there. Essentially, you carry out measurements of the extremes, which might be minimum thicknesses or maximum depths, and extremes on grids of a common size. So depending on the underlying distribution, those extremes will conform to one of a limited number of extreme value distribution types. And if you can establish the parameters for those extreme value distribution, or for the extreme value distribution, you can then make estimates because you've got a full description, statistical description of the behavior of minimum thickness or maximum depth, for example. So what we'd be doing looking at the underlying distribution is taking lots and lots of measurements using corrosion mapping typically, and you would then develop that full underlying probability distribution. With extreme value approach, you would be basically typically dividing the area up into grids and just taking a minimum thickness or a maximum depth within each grid, and then your distribution is based on those maximum wall loss in this instance. So here we might have millions or tens of millions of data points that go into defining the distribution. Typically within an extreme value distribution, we may have tens or hundreds or thousands of points maximum in the distribution. So you can see you get a lot more information when using the underlying approach. So the extreme value distributions that are typically used are type 1 distribution, which some of you may be familiar with as a Gumbel distribution, and that really kind of plots largely linearly on a log scale. It's close to exponential fall as you go down the distribution. That's quite widely used for situations where the underlying distribution would be exponential, and then a Weibull distribution is lighter tailed. In other words, it drops faster than the Gumbel distribution. This graphic also shows a type 2 extreme value distribution, which is referred to as also as a Frechet distribution. Basically what that's showing is that there's a sort of increasing likelihood of, or certainly by comparison to the Gumbel distribution, of having severely or significant depth of corrosion. So typically for statistical applications, if you get any indication of a heavy tail distribution like this, either within the extreme value or in the underlying distribution, that's a situation where you wouldn't be comfortable applying statistical analysis because it becomes very difficult to quantify the reliability. You've always got a likelihood of having quite significant corrosion or much more significant corrosion in the area that you haven't inspected. So just looking at practical application of the extreme value distribution or extreme value approach, you'd carry out inspection on grids, record the minimum thickness within each of those grids. You would then fit an extreme value distribution to the minimum, which in this case we've carried out here. So basically fitting an extreme value distribution to the measured values, which are shown by the blue dots. And this plot basically shows what's the probability associated with a randomly selected grid. So if we took one grid at random, what's the probability that the minimum thickness would be less than the given value? We can also extrapolate from that to carry out estimation. So now we've carried on much further down the probability axis and thickness axis. And in this case, for instance, we might be interested in what's the minimum for 100 grids. So that's indicated by the red dot, which corresponds to a probability of 0.01, which is well, that corresponds approximately to the probability level for 100 grids, which is 1 over 100. So from that extrapolation, we can then say that the minimum thickness that we'd expect for 100 grids would be about 10.4 millimeters. So the kind of estimates you can do with an extreme value distribution, it allows you to estimate the minimum for a given area. So essentially, you look at the extrapolation to a probability level associated with the number of grids. So for a situation where we have n grids, we'd be looking at a probability level of approximately 1 over n. And that's the most frequently occurring value if you were to take the minimum of n randomly generated samples from the extreme value distribution. In practice, obviously, the minimum can be more or less than this because that's really a statistical estimate. So it's also useful to try and understand the probabilities for the actual minimum being less than a specified thickness. And that's determined from the equation which relates the probability of the minimum for n measurements to the cumulative value for the underlying distribution. So once you've established that initial distribution, you can then make estimates for the minimum for a much larger area. I think it's worth also saying that the estimates from an extreme value distribution are not always very precise. Sometimes people put a lot of store by the minimum thickness estimate based on an extreme value distribution or even other statistical methods without saying, well, how good an estimate is that actually likely to be? So that's possible using the process that I've mentioned on the previous slide to establish what those distributions are. If we look at the graphic on the left here, the distribution shown in red indicates the probability for the minimum of 100 grids. So we can see that that peaks at around 10.4 millimeters. But there's a significant probability, in other words, a large area under the curve to the left, and that's about 63% likelihood that the minimum would be less than that expected value. And even if you follow that curve down to 9 millimeters, for instance, there's still a reasonable likelihood, in other words, reasonable area under the curve, that the minimum could be less than that. So that's illustrated, I think, a bit better on the graphic on the right, which showed the red line there shows the probability of shortfall for the minimum of 100 grids in this case. So essentially what we're saying is that there's a 10% likelihood, so looking at the red dot on the left, that the minimum would be less than about 8.2 millimeters, and there's a 10% likelihood, looking at the red dot on the right, up at the 90% level, so there's a 10% likelihood that the minimum might be more than about 11.2 millimeters. So there we see there's like a range of minimum that we can expect, which would be at the sort of 80% range from 10% to 90%. So that can be thought of as like an 80% tolerance based on the statistical estimate, which is 3 millimeters in this case. So just because you've been able to make an estimate of minimum thickness doesn't mean that there's a high probability that the actual minimum will be very close to that. And it's important to understand what the variability is likely to be. So the analysis should consider potential errors and uncertainty. The primary sources of error that you need to consider are the distribution. Is the distribution that you've selected actually, is the data a good fit to that distribution? Is the data likely to come from that distribution? Sometimes it's possible to select the wrong, like an inappropriate distribution, and that has an impact. Errors can also come from selection related to the sample size. So if your sample size is very small, there's more variability around the fit of the data related to that. The method of fitting the distribution to the data, how do you solve within the distribution parameters? That has a major effect. There's different methods which will give you different results. Also, what's the local variation, like how homogeneous is the situation? And then also the measurement itself is important. Large measurement errors will tend to feed into increasing uncertainty, and more accuracy will tend to reduce the uncertainty. All of those errors tend to be magnified with the extent of extrapolation. So as you increasing the area that you are interested in trying to make estimates for, so the amount of uncertainty tends to grow. But it is important to understand the contributors to those errors and evaluate those effects before making decisions. A lot of, I guess, emphasis when it comes to statistical analysis is around the topics that I've already discussed. In other words, how do you actually fit, what's the basis for fitting distributions? How do you make estimates based on those distributions? But ultimately, if you want to get value out of an inspection with limited coverage, the planning for that inspection to actually give you the kind of information that you need is really important. And you can maximize the value of the inspection by carefully planning the inspection. The starting point for that is obviously what is the objective of your inspection, and that should be clearly defined. And you need to consider the objectives really at two levels. At a high level, what integrity management requirement are you trying to satisfy, and secondly, how do you provide enough information to base the integrity management decision, on which to base an integrity management decision. So a high-level objective might be to validate the condition of a vessel based on NII, and the detailed objective would be that the inspection must give you enough information to make estimates of the minimum thickness. So the next few slides I'll go through fairly quickly, just looking at some of the key factors in planning for inspection. The expected corrosion conditions are critical, and how much coverage, for instance, you would need depends very strongly on the corrosion conditions. It's also important to recognize that the analysis of data is for specific process zones, so you should restrict an analysis or a data set to a particular process zone, otherwise you sort of mixing different distributions potentially. So within each process zone, the density and homogeneity are key considerations. So density, really what we're talking about is how much of the area is affected by corrosion. If you've got a high density, like the image on the left here, where 90% of the area is affected, you're getting a lot of information from a relatively small area, so you could end up with, well, you could do a low coverage and achieve a lot of information. The graphic on the middle shows a situation where there's 10% of the area affected. So there, in order to gather enough information, we'd be looking at doing more coverage certainly than in the case of the high density on the left. And then the graphic on the right there shows a situation where only 1% of the area is affected, and now we'd be having to do a pretty high coverage in order to achieve the same level of information on the degradation state. So density is really critical to, or an understanding of the expected density is really critical to defining how much coverage you should be doing. The density also affects the scale of homogeneity. Where you've got a high density, generally speaking, like in the figure on the right, pretty much any reasonably small sample area that you look at there is going to look largely like any other reasonably small sample area that you consider. You don't have to go to a very large size in order to get them to start looking similar. Whereas if you look at the graphic on the left there, where there's just a small number of corrosion points, we'd have to take, well, in this case, even taking that full area wouldn't necessarily guarantee us that if we were to take another area now outside of this, that we're going to be seeing something that's looking fairly similar. So where you've got low density, in order to understand if you have got homogeneity, and in order to ensure homogeneity within the total sample, you have to take a much larger coverage. So the scale of that variation is also important with respect to the inspection region sizes, and that's illustrated here. So we have here two situations where we've got the same density, in other words, the same number of corrosion points in both of the graphics, but the one on the left is more within a certain area. It's more likely to hold the same number of defects with it, whereas the one on the right, you can see if we were inspecting only an area indicated by the green and the red boxes, we could easily run into a situation where we either capture a very high density of corrosion, which would be unrepresentative of the situation overall, or we might even put that box in an area where there's no corrosion at all, which would give us a completely wrong impression of what's going on, and obviously an unrepresentative statistical analysis. So in general, it's much better to collect the data in the form of a large number of smaller areas than one very large region. It's also worth saying that up front it's difficult to understand what the density and homogeneity are likely to be unless you've got additional inspection information. But once you've carried out the inspection, that itself, the data itself, gives you a basis for understanding the effects of spatial variations on estimates. So one way of doing that is to take multiple samples, or taking regions from different parts of the total inspected area, carrying out an analysis for that subset and looking at what the results are for each subset. And if there's a lot of variation based on your subsample, that would suggest that the results are more likely to be spatially sensitive. So you can carry out those kind of sensitivity studies. A key issue in planning for inspections is coverage. So the reliability of your estimates depends on the nature and distribution of coverage, and also what's the degradation spatial characteristics, which we've looked at to some extent already, so things like density and homogeneity. So it's important to recognize, or just emphasize again, that it's not the total amount of coverage that dictates how reliable your estimates are going to be. It also depends, the coverage varies, an appropriate amount of coverage varies according to the degradation state, and also how you actually spread that coverage. As I say, lots of small regions is better than a small number of large regions in general. But there's also practical factors to consider, like access and surface condition. Surface conditions is often an issue when you've got aging assets, as shown in some of the pictures on the bottom left. Measurement accuracy is also a major consideration. Poor accuracy adds noise to the data, and essentially what that does is it spreads open the distributions typically and makes for greater uncertainty and less reliable estimates. And in general, there's a trade-off between coverage and accuracy. So by increasing accuracy, in many cases you can reduce the sample size that you need in order to give you the same level of reliability of estimates. So there can be a cost benefit to more accurate and reliable inspection. It's important to do trade-off studies at the planning stage to understand what does represent an appropriate level of coverage with a given accuracy. And there are some practical issues that affect accuracy. It's not a one-size-fits-all kind of number for a given technique. There's things like degradation morphology and surface condition. I won't spend too much time on this slide. I think basically what I was trying to say is it is important to quantify measurement performance, and because that does affect the reliability of your statistical estimates. There are significant amounts of data available via blind trials carried out in the HOIS Joint Industry Project, for example. There's also some data published in the HOIS Recommended Practice for Statistical Analysis of Inspection Data. It's important to say, however, that you need to be careful using generic values. And it's much preferred to quantify performance based on actual field data where possible, because the field data won't always achieve the same or similar performance to sort of generic values that might have been developed within blind trials. And there are methods of evaluating accuracy of actual field data based on analysis. So the next few slides look at some applications of sampling inspection. I'll try and go through these fairly quickly, seeing as we had a slow start or late start. Non-intrusive inspection of pressure vessels is a major application for statistical analysis, and it is fundamental to type B NIR strategies within the HOIS Recommended Practice for NIR, which is published as DNV RP G103, and that's a widely used document for planning and evaluation of non-intrusive inspection of pressure vessels. So the basic principle there is to use sampling inspection. In other words, your inspection work scopes would typically have less than 100% coverage, and then there's a statistical analysis of those results, which forms part of the justification that the NII has achieved the integrity objectives. Another area where we've, in Sonomatic, have been making use of statistical analysis is for storage tank floor inspection. Historically, storage tanks were taken out of service for floor inspection, but robotic in-service inspection of storage tanks is permitted in APR 653, and there is a requirement there for statistical analysis of the sample data. So you wouldn't be carrying out 100% coverage of the tank floor with the robot in the liquid in the tank. Typically coverages are much lower than that. So Sonomatic does provide in-service inspection of tank floors using a statistical basis for looking at the condition of the tank floor. And we've recently completed inspection of a crude oil tank, 80 meters diameter, where we did 500 runs distributed over the tank floor, each of those runs at a high density of accurate wall thickness measurements using 0-degree ultrasonics. That was about 4% coverage of the tank floor, and we used statistical estimates to make statistical methods to make estimates of minimum thickness and probabilities associated with it. And that was able to show the floor was in an acceptable condition, and we could derive a inspection interval from that. So other applications are in-service inspection of FPSO tanks, and that allows you to, the approach is similar to NII for vessels, and that allows you to carry out inspection with the tanks remaining in service. Slug catcher inspection, again, this is a case where there's a large area of interest, and 100% coverage with accurate inspection techniques wouldn't be economically feasible. So statistical methods based on sample inspection allow you to do a cost-effective approach. Pipework inspection, I mentioned sampling has been widely used in that environment without necessarily a formal statistical backup, but more detailed statistical analysis does build an understanding of the effectiveness of different strategies, and also helps define efficiencies or drive efficiencies. So this is becoming much more widely used now within pipework inspection, assessment, and evaluation and planning. And then finally, unpiggable pipelines, basically where you're going to be, you don't have access for pigging, so you're going to be doing external inspections, and typically you can only achieve low coverage driven by economic requirements. So that's been fairly widely used for planning and evaluation of inspections where the aim is to validate absence of degradation, and also in some cases where degradation is present. But pipelines you need to be cautious with because the coverage tends to be very low. So issues around homogeneity and so on become very important. So this slide, I just wanted to give it an overview of the benefits and looking at like what is the level of acceptance and change of acceptance within the industry. So I think from what we've covered, we can say application of statistical analysis does provide a more reliable view on the current condition and remaining life. It ensures the value of inspection data is maximized, leads to more effective integrity management decision making with a positive impact on business and HS&E goals from for operators. These statistical approaches are not yet very commonly used. In other words, not necessarily an everyday application all the time within integrity management, but there is growing interest from industry, and that's indicated, for example, by the level of activity within the PRCI, which is Pipelines Research Council, and also within the HOIS Joint Industry project. The benefits are significant, and operators are increasingly recognizing these benefits, and there's been a clear shift in acceptance over the last 5 to 8 years, where there's a growing number of operators now making substantial investment in capability development, and I think there's a recognition that data analysis is an increasingly important part of integrity management. Another aspect of it is that there are inspection technology developments which basically make it easier and more cost effective to get high density data sets, more quantitative data, and also the sort of evolving developments in statistical analysis means that the application is growing rapidly. So it's kind of a changing landscape in terms of integrity management. And really this slide, which is my last slide, I guess gives an overview of some of those changes which are being driven by increasing access to more quantitative data, plus also a recognition of the benefits of more advanced analysis. So the inspection technology plus data science kind of coming together in the same way that data science is affecting efficiencies and approaches across many other areas of industry where there's a greater drive towards using data and data-driven decision-making and management. The same thing is starting to happen within integrity management. Now, I won't go into the details of all the information in these boxes, but really the kind of direction integrity management is going is where you have more detailed planning process with clear objectives, quantified performance requirements. So a lot of emphasis on more data, quantifying performance and so on. The inspection technology, as I've mentioned, is evolving very rapidly and allowing us to get more and better data at lower cost. Data that's being backed up by data science to maximize the value of any data that is collected. And then also integrity management systems are evolving, and RBI systems, for example, are evolving to make better use of more quantitative data. There's probably a long way to go in some of these areas, particularly in the way RBI is used, for example, and even some of the simple steps that can make a big difference is just making use of data that you have to update the RBI rather than seeing it as something that's essentially static, and quantitative data and analysis gives you a much stronger basis for doing that. Right, so that covers the presentation, and I'd like to thank you all for your attendance. Apologies again for the glitches in the beginning. We thought we'd figured it all out when we'd done some trial runs earlier, but obviously there were some additional hiccups along the way, for which we apologize. But yeah, thanks again for your time, and we appreciate your attendance today. This webinar, maybe with some cleaning up in the beginning, will appear on our website quite soon. So that's the Sonomatic website, which all of you are familiar with, hopefully. And if you've got any questions, rather than us trying to challenge ourselves with the technology any further now, I think the best will be to get in touch via email on info@sonomatic.com, or if you've got my own sort of Sonomatic email address, or you can get in touch via LinkedIn, you're welcome to do that, and I can try and answer any questions. Right, thank you very much, everyone.